Hello, my name is Shruti Vinod, and this is Lab Report 5 for Physics 2212. Now, the purpose of this lab was to understand the properties of Faraday's law using a bar magnet and a tube of aluminum foil. And the overview is that the average time in the experimental model for the magnet to fall through the tube was 1.341 seconds. And in the competition model, it was 3.1015 seconds, and there was like a 76% difference between experimental and computational models. And the fundamentals of physics laws that we use here were Faraday's law and gravitational force. So, background and experimental setup. So, the system was a bar magnet, and the surroundings was an aluminum foil, and the corresponding magnetic field that comes from it, and Earth's gravitational pull. And the initial conditions are that the magnet is held above the tube at rest before being dropped through the tube. And a summary of the experiment is that you drop the bar magnet north side facing down through a tube of aluminum foil and record the amount of time it takes for the magnet to pass through the tube, and you repeat this 5 times. So, the model. The objective was to find the amount of time it took for a bar magnet to fall through a cylindrical roll of aluminum foil, and our average time was 1.341 seconds, as shown here. We have a trial, start-end time, and elapsed time. And the magnet basically would linger in the middle of the cylinder due to the induced magnetic field, as its flux changes due to its movement, and this magnetic field briefly counteracts with the Earth's gravitational pull. So here I will talk about the parts of the coding that I tweaked. So here we basically changed the values to according to what we had for the geometry of the tube. So the length, width, and the inner radius. And then the next part that I changed was the properties of the magnet. So we had the mass of the magnet and then the mu mag from the previous experiment that we had. And then we also changed the part to calculate the dipole electric field. And we also calculated the flux, and the part that was supposed to be added was the denominator. So here we have the radius of the ring squared plus the distance squared, and it's all to the power of 5 halves. And we also added the next one line to calculate the gravitational force on the magnet. And this 4 lines of code were also changed to find the electric field at the ring and the direction vector of the electric field, and finally, like the magnitude of the force on the ring. Then we have one more line that was edited to find the overall net force on the magnet, and we also had to tweak what the velocity and position of the bar magnet was. So as you can see here on the right, there's a picture of the computational model with the red ring representing the North Pole and the blue ring representing the South Pole of the bar magnet, and the position of the magnet changed as it fell through the tube. And here to the left is the graph of the velocity versus time. And as you can see, this was according to the mu value, and this was not really the graph that I was expecting, because the time was much lower for it to fall than it had been in the experimental version. So, like an explanation for this results would be that the stagnation of the velocity comes from the principles of Faraday's law, and as the magnet approaches the magnetic field of the aluminum, it causes a change in flux. And due to the change in the flux, there's an induced EMF or electromotive force. This induced EMF causes the magnet to stagnate in the middle, and the velocity will eventually increase again as it exits the tube. So, similarities and differences between the code and experiment stuff was that the velocity of magnet in both computational models stagnated as the magnet approached the middle of the tube. However, the time it took differed by like 76% between the two models, and this could be due to the computational model assuming that the magnet begins falling directly at the point of entry, whereas in our model we dropped the magnet maybe 2 to 3 inches above. And potential source of error was that aluminum foil wrapped around a paper towel is not really going to be as strong as a conductor as compared to a model, and that this is an open lab, so it doesn't guarantee or like any assumed magnetic field of both of the foil or magnet. What if the resistivity of the conductor was reduced as close to possible as zero? How would the dynamics change? A higher conductivity would lead to a stronger induced EMF. The velocity of the falling magnet would slow very close to zero. And what if holes or slots were cut into the tube? Well, how would this affect the current rings? Without consistent rings to conduct an EMF, the induced B field and magnet would not be strong. In the model, the current rings would be weaker. Thank you.